Hello, now study to introduce a slightly different way. Previously, this recombined I statistics is not only designing, constructed an estimator that is simultaneously for semi-parametric distributions and for parametric distributions, but it also reveals that because its excellent performance it reveals that a relatively invariant structure among the unimodal distribution, and in addition to the ordinals, another distributions that is very unique to this is that it's basically saying that if we set the d even as a constant, and then the resulting this structure will be the value is very invariant, consistent to the mean. The bias is invariant, relatively invariant, although not very strictly invariant, relatively invariant for most common unimodal distributions over high kurtosis. And the recombined I statistics, if we modify, instead of we can plug in the LU statistics into cumulative distribution function, and then we can construct a quantile I statistics. For example, yes, for example here. Yes, for example here, for example, 0.5. If you, for example, the trim mean is 0.5. If you plug in into a cumulative distribution, 0.6. For the medium, of course, it's 0.5, the percentile. And then you can computing the differences between the percentile of medium and the trim mean of medium, and then times the d value plus the trim mean. Okay. The resulting, it depends on the d value. For example, maybe 0.8. And then we can use a quantile function to estimate the quantile 0.8, and the resulting it can be also similar, be a consistent estimator for 5 if setting the exponential distribution as the consistent distribution for this 5 two-parameter distribution for some special cases, and also yes, and for the quantile function you need to carefully consider the quantile function and the empirical cumulative distribution function. It is this two. The first is very popular, proven by Hedman and Fan in 1996, and another is also very popular. It's just linear interpolation of modes. And these two, innovation here is that I deduce the inverse function of this quantile function, so forming a cumulative, empirically cumulative distribution function that has minimizing the finite sample bias. And then we can say that because there is another issue that what kind of robust location estimators we use. Normally, because the medium is because the robustness is closely related to the bias. So in most cases, if you just consider the bias, using medium as the most biased estimator is normally the best choice. Normally, if you just consider the bias, the problem is that how to choose another estimator, but we need to consider that, for example, first that the most important thing we need to ensure is that this mean, for example, this is the medium, and this is the mean, medium, mean. Median and mean. The issue is that first, because of the structure of this recombined I statistics, we need to ensure that this recombined I statistics, the LU statistics, is within this interval. So it must hold an inequality. So this is why we previously so careful about discussing the ordinals and U ordinals, and because the deduced mean estimator can ensure this inequality under the assumption of U ordinals, nuth ordinals, U ordinals, and so this is if the distribution follow that ordinals, nuth ordinals, the related estimators will follow this inequality. And also, most of the time, we hope that these estimators can be, yes, and also we consider in other cases that an advantage of this inequality is that even it does not follow for example, the nuth ordinals. There's an issue. For example, maybe even in some cases, the symmetric quantile average function, it is not monotonic. But however, you should remember that the weighted average, it is it is over. For example, if the trim proportion is 1/8. And then it is here, and the mean is over here, the integral, the symmetric quantile average. So because this part is monotonic decreasing, so that means the mean will be always greater than this estimator. And also medium is here, and because this is also monotonic, so and so we can expect it that this will be, and this is a relatively small proportion, so we normally can expect it that this estimator will be higher than the medium in most cases. So that means that this that means this mean weighted average and medium inequality, it is slightly robust to the fluctuation, to the violation of these ordinators. Yes, as I showed an example, even even third ordinators, it is valid. It is slightly robust. And also another thing we determine is the schooners. That previously we already discussed that for a very School distribution, highly School distribution, it will eventually order it. And then so the violation normally occurs when the distribution is symmetry. But you should remember that for a relatively symmetry distribution, the medium, mean, and the trim mean, even it is not follow this inequality, but they should be very close because it is a relatively symmetry distribution. So that means, for example, maybe if we correct it, this is medium to the trim mean. If we do a correction, for example, maybe to here, and then the resulting maybe recombined mean is this here. But this is a wrong correction, right? This is a wrong correction. The mean is here. But this differences, it won't be very large because this distribution is nearly symmetry. So this that means this estimator it will have a very small bias for distributions that is valid for the ordinators and Knuth ordinators. But even for in some cases that it does not follow this, the ordinators, but as long as maybe for example, especially if it is unimodal, and then this violation will be very small. So it will not. It is of course not the best choice. The trim mean will be more medium will be better, might be better. But this will still return a result that is a relatively not very bad result. And and also the reason that I consider this trim quantile I-statistics is that because later I consider because we already converted the estimations of central moment into estimating the location of a central moment kernel distribution. So this is the central moment kernel distribution. You're just estimating the location, this location, and then you can get and then you can get the result. The issue is that if we try to convert, if we try to use the recombined mean to estimating this central moment kernel distribution, and then you will get a result. And then this result, of course, it is much better than the trimmed central moment or medium central moment, or some if you're using other popular non-parametric approach. Of course, it is much better. But however, because the central moment is a highly kurtosis, the kurtosis is very high normally because this was due to it is a very high kurtosis. There is a very heavy tail. This is due to it basically converted each pair with the for example, for the second central moment there is a square. And for the third central moment, there is you need a power 3, and for the fourth power 4. So it will amplify all these values, and also sometimes shrinks all these values. And especially for the even central moment, it is inherently be an asymmetric distribution. So this for such a very School distribution, as we showed previously, that here the major advantage of the quantile mean is that although for example, for this distribution, you can see that the quantile mean may have a larger bias, the orange, comparing to the recombined mean. However, for the Pareto distribution, this kurtosis is much higher. The quantile mean is slightly better than the recombined mean. And if the kurtosis is even higher to 50, 50, and then 50 to 90, and then this advantage will be amplified. So this is why we introduce this quantile I-statistics here. But a drawback of quantile I-statistics is that we must ensure the computing, the result is within the breakdown point. For example, if you 0.6, yes, for example, if this d value, if you returns the result 1.2, and then it is not valid because quantile must be smaller than 1, right? And even if it is smaller than 1, it is still not valid because if the quantile 1, it is not robust. It is not robust. So it must be smaller than the breakdown point. We suggest, for example, if the breakdown point is 10%, and then it must be smaller than 0.9. And indeed, in some cases, this might be violated. For example, if you set a d value for this d value for a central moment kernel distribution for the Weibull distribution, and then using this d value to estimate the Pareto distribution or gamma distribution, and for some high kurtosis scenarios, this d value might return a result that over the breakdown point we suggested, especially if this breakdown point is relatively large. And so this is an issue, and a possible solution, although not very good solution here, is I just modify. For example, if it returns 0.95, but the breakdown point we want is 10%, and then I just modified it at 0.9. So this is my solution to this issue. And here, and when we consider whether we can, but there's an issue that, especially as I said, if this quantile mean and recombined mean is already very optimum very best for this in estimating the mean if just using the exponential distribution, because the unique structure of this exponential distribution. But however, if you consider higher central moments, and then you can see the result is no, not showing here. Generally, if using higher central moments, the result is not as desired. So we need to further consider whether it is possible to using a shape scale distribution. So instead of using a location scale, we're using a shape scale distribution. So using a shape scale distribution has an advantage that, for example, if we can estimate the schooners, and then if we know, well, this distribution is nearly symmetry, and then we can further returning a smaller d value, and then this overcorrection can be even smaller, right? Yes, and so in this way. And it is possible because we first generated the d-value function. This d-value function will increase as the kurtosis increase. This is first know a d-value function, and then this d-value, and then the recombined moments, this d-value function, and then the recombined moments. It will and then this is it is indeed just finding the solution of the systems of equation, and this is an overdetermined nonlinear systems of equation. So we need to separately determine it. First consider the schooners, the above, and then consider the kurtosis. For example, if we here is my algorithm. This algorithm was inspired by the Huber M-estimator because it is very similar to the iterative reweighting. The method is that we first determine a kurtosis. I just use the maximum kurtosis available. For example, maybe 90, and then you use 90 kurtosis. There is a d-value. You're using this d-value, and then plug in this d-value. And then first, of course, we need to computing the medium central moments and another weighted Hodges-Lehmann central moments. This related, but you know the d-values, and then you can computing the recombined third moment and recombined second central moment. And then if you're using this, you can if you're using this, you calculate it. You can obtain a recombined schooners. You can computing a recombined schoon. This recombined schooners, you can further use this. Here is the kurtosis. Or you can obtain a recombined kurtosis. You can use this newly defined recombined kurtosis. Although this is wrong because it is from a larger d-value. This d-value is overestimated, but we can re-guess it. For example, the first guess is here, maybe 20. The second guess might be maybe 12. It will be much smaller. If the true guess is 9, and then smaller, and then it will greater generally converge. And this theorem shows that it is a consistent estimator, and it will converge because it is the largest attracting fixed point. And but we need assuming that the medium central moment is 0, and gamma is equal to 1, and also this U congruentness. And then this and then we can say that all this and then we can suggest it that all these methods, of course, here is the iterative reweighting, and after using this method, as I show here, for example, for the recombined variance, recombined third moment, you can returning a very small, 0.005. And also for this recombined third moment, it is very small for the quantile fourth moments. And generally, these bias are very small. This bias is a result that the weighted average of the bias of weighted average of all 5 two-parameter distributions. Yes, and so because if you don't use a two-parameter distribution, just use the exponential distribution, this value is about 0.4, if I remember correctly. Yes, generally very large, and this is very small, and just 2%, 3%, and indeed it can be even better. And but before that, I would like to first another candidate called multiple consistent distribution, and this is that for example, if we if we use a shape scale distribution as the consistent distribution, then for each schooners will corresponding to a kurtosis. So there is a one-to-one corresponding between the schooners and kurtosis. But if we use a this indeed reveals that this is why we separately estimate the kurtosis and schooners, because it is very likely that we estimating the schooners and kurtosis, it does not fit the relation we want, the schooners and kurtosis relation we want, because it is from the sample. And then, if we consider using multiple consistent distributions, for example, this is the multiple consistent, and then for example, this is the kurtosis. We first draw a graph that kurtosis, schooners, kurtosis. Schooners, kurtosis. This is the schooners, kurtosis diagram, and we first consider that, for example, if we estimating schooners and kurtosis, if the point is here, And then we can guess that because we now use two different distribution as the consistent distribution, we can measure the point of this kurtosis and Schooners, measure the relative difference, for example, to this first distribution and the second distribution. We can measure using some distance measures to estimate the closest distance, and then we compare this distance to this to which whether he closest to which distribution. If it is to this distribution, the first distribution, and then we will use this distribution, the d-value, as a consistent distribution. We further reweight it using this algorithm. If it is closest to the second distribution, and then we use this second distribution as reweighted. So generally, it will also be an iterative reweighting, a little bit like this. Yes. Yeah, so generally, if you closer and closer, you will converge to the true value using iterative reweighting. Or even if the result is relatively middle, and then it might be it might returning some average result. So generally, this method we can extend it to even multiple consistent distributions, and theoretically it is possible we can construct an estimator that is simultaneously consistent for all these 4 and even 5, including the general Gaussian distribution, all these 5 two-parameter distribution. It is possible, and there is no bias for this all these 5 distributions theoretically, and